Okay, we want to continue chapter 33, sound waves. Today we will talk about regular and irregular vibrations and the three properties of notes. Let's start. Do you remember the meaning of vibration? Here in this chapter, vibration, it is what? It is the thing that causes sound. If there is no vibration, there will be no sound. Okay? So, we have two types of vibrations, regular and irregular. Irregular vibrations, such as those of motor engines, cause noise. Regular vibrations, such as occur in the instruments of a brass band, produce musical notes. So, we have regular vibrations, irregular vibrations. Regular, like what? What do we call them? Musical notes or a note. Irregular, what do we call it? Noise. Now, what we are going to study is what? Regular vibrations. Musical notes. They have three properties: pitch, loudness, quality. Okay? We are going to study each one alone. But before we study them, let's watch this video about noise and notes.
Both noise and notes are mixtures of sound waves at different frequencies. A note is made up of a ripple pattern which repeats itself over and over again in an ordered way, while a noise is made up of individual ripples which have no relationship to each other and do not repeat, and so are disordered. If an object moves,
Okay, that's all about noise and notes. Okay, the first property of a note we want to talk about is pitch. What is pitch? It is the frequency of the sound wave. Do you remember the meaning of frequency in sound waves? The number of compressions per second. So, the frequency of sound wave, here what it is? Pitch. So, pitch will be higher when vibrations are faster. So if we have more vibrations, the number of vibrations is more. So here it means that what we have a high pitch because we have high frequency. So the relationship between frequency and pitch. Frequency is higher, it means pitch is higher. Wavelength is shorter, it means pitch is higher. But pitch depends on frequency. More frequency, more vibrations. Here look, the number of vibrations here more than the number of vibrations here. So this one has higher pitch, this one lower pitch. Pitch, like color in light, both depend on frequency. Do you remember in light waves, we said that frequency, light of any color, the color of any light depends on the frequency, not on the wavelength. The same thing here, pitch depends on frequency. Let's watch this video together.
What I would like to discuss now is the relationship between frequency and pitch. Now you know that this sound, for example, has a lower pitch than this one and a lower pitch than this one and so on. And what happens really is that the lower the frequency, the lower the pitch, and the higher the frequency, the higher the pitch. Now there's also a very interesting...
So here, what's the difference here? Here we have the same piano. What is the difference between these lines? The difference is what? Of number of vibrations. Some of them the number of vibrations is more of the other. More vibrations, it means more frequency, more pitch. Okay? Here's an amazing video about high and low pitch. Watch it to understand.
Hi, I'm Jared. Welcome to Fun Science Demos. And the big idea today is sound and how sound changes. Through science, we've discovered that the faster something vibrates, the higher the sound or pitch. And the slower something vibrates, the lower the sound or pitch. I can show you with my voice. La. My vocal cords are vibrating slower. La. They're speeding up. La. Speeding up. La. They're moving really quickly, so the pitch goes up. I can't show you that through my throat, but I can with these neat little demonstrations. I have rulers fastened to the tabletop. I have a guitar. I have a xylophone. And I'm going to fill a bottle of water to show you that science at work. So let's use these rulers. Again, the slower something vibrates, the lower the sound or the pitch. I can even see that ruler moving slowly. Well, the faster something vibrates, the higher the sound or pitch. Low, high. Slower, faster. Let's check out the guitar. Let's see if we can make that pitch higher by making it vibrate faster. The pitch goes up, the faster it vibrates. Now, let's try the xylophone. You can hear the sound and the pitch go up because that's vibrating much more quickly. This is vibrating slower. Slower.
I hope that this video helped you to understand the difference between high and low pitch. Okay? Let's talk about something we call it tuning fork. Tuning fork has two steel prongs which vibrate when struck. The prongs move in and out together, generating compressions and rarefactions. So this tuning fork, only when it vibrates, it causes sound because of vibrations. It generates compressions and rarefactions. Also, let's watch this video together.
We can record pressure variations in sound waves with this kind of instrument, an oscillograph. Sound waves are striking the diaphragm at the left. The stylus records the sound waves as a graph. Later we shall use such graphs to represent sound waves.
Okay girls, before the video continues, I want to explain to you something. What is represented here? It's not the sound wave. We know this. You know that sound wave is not a transverse wave. Here is the sound wave. Here is it. It works as compressions and rarefactions. It moves back and forth, okay? But here it's a device, we use it to represent sound wave. So we can study it, we can understand it, okay? So you can say that sound wave is a transverse wave. Here it's not the sound wave. The sound wave is here. Because of the motion of the sound wave or the vibrations, we use this device to draw or to represent sound waves. When the video finish, I will continue explaining to you.
Stylus records the sound waves as a graph. Later we shall use such graphs to represent sound waves. Condensations cause the stylus to move upward. Rarefactions cause it to move downward. So far we've seen how sound waves are produced. Next we'll identify three auditory effects of musical sounds: loudness, pitch, and quality. We begin with loudness. Every sound sets up a disturbance in the transmitting medium. The larger the disturbance or displacement of the individual particles, the greater is the height of its graph above the neutral line. This displacement above the neutral line is called amplitude, and it is amplitude that determines loudness. as its loudness increases. Next, let us consider pitch, the auditory effect of frequency. First, we hear the sound of middle C. Next, we hear G below middle C. And now the sound of C below middle C. What causes such differences in pitch? To explain such differences, we picture two different sound waves. Here, the lower fork makes more complete vibrations per second. Therefore, its frequency is greater. It is evident that the one with the greater frequency has the higher pitch.
Okay, girls, I want to tell you something to understand more about pitch. Now, if you have, for example, a rubber band, when you stretch the rubber band a lot and you try to vibrate it, you will feel or you will see that it vibrates a lot. When you just stretch it a little bit, okay, it will vibrate a little bit. So here's the relation. When it vibrates more, it means what? It means that when it vibrates more, it means that it has higher pitch. When it vibrates less, it means it has lower pitch. Okay? The same thing for tuning fork. Now what I want you to know here, as I said, this is a sound wave. It is a longitudinal wave. Compression, rarefaction. Compression, rarefaction, all the way. Now here sometimes they represent sound waves as a transverse wave. Here we are not representing the sound wave, we are representing the pressure of sound wave per time. What happens to the pressure while the sound wave or the air of the pressure of the particles of the medium while the sound wave is moving through this medium? So the area of compression where the particles are close to each other, it means here we have what? High pressure. The particles where are far away from each other in rarefaction, here low pressure. Okay, so the peak or the crest here, the top, it means what? High pressure. It means on the sound wave compression. The trough, it means rarefaction. This is very important. They ask a lot of questions about it in the exam. Okay? Don't forget, always when you see a sound wave looks like that, it means that here they are talking about the relationship between pressure and the pressure of medium of a sound wave. Clear? The second property we want to talk about is loudness. Now, pitch depends on frequency. Loudness depends on the amplitude. Remember the meaning of amplitude? It's the distance from the equilibrium line to the top of the wave or to the crest. This distance we call it amplitude. The higher the amplitude, it means the louder the sound. So what's the meaning of loudness? How loud the sound is. The amplitude of the longitudinal sound wave. Okay, it depends on the amplitude of the longitudinal sound wave. Now, what does it mean, louder sounds? Now, louder sounds, it is when more sound energy enters our ears per second than before. This happens when the source is vibrating with a larger amplitude. You remember in pitch we said more vibrations, it means more frequency, it means higher pitch. Here we are not talking of the number of vibrations, we are talking about the energy of the sound wave, the energy of this vibration, okay? Energy, it means amplitude. So the higher the amplitude, the higher the loudness, okay? Let's watch these two videos.
Louder sounds are produced by inputting more energy into creating the wave, whether it be shouting louder, hitting a drum harder, or plucking a string harder.
Okay.
The energy is transferred by a bigger vibration.
You see, just the same object, same material, we just put more energy. So if you want to shout, what do? You put more energy to shout, okay?
wave. So how about loudness? So this note here is the same pitch as this one, but of course there's a difference, right?
What causes the difference here? That in each case we put more energy, louder sound, okay? The last property we want to talk about is quality. Focus please to understand quality. Before I start reading, I want you to watch this video.
The third characteristic of sound, that is quality. For this, let's listen to some music. Is it a single instrument or are two instruments playing? For sure, there are two instruments playing. One sounds like a violin and the other one a sitar. Both the instruments were producing their sound with the same pitch and loudness. But still, we could identify the difference in the instruments because of the type of sound they are producing. The sound produced by every instrument has a unique characteristic that distinguishes it from other sounds with the same pitch and same loudness. This characteristic of sound is the quality or the timbre of the sound. The sound which is more pleasant to hear is said to be of a rich quality. The sound produced by both the violin and sitar are pleasant to listen to. Thus, these sounds are of rich quality. On the other hand, the sound produced by a tuning fork is not pleasant to hear and hence is of poor quality.
Okay, let's start now. The same note on different instruments sounds different. We say the notes differ in quality or timbre. The difference arises because no instrument except a tuning fork emits a pure note of one frequency. Look here. Now here it is a regular vibration, girls. It's not irregular. Why? Because we have one pattern repeats itself. And here's the wave. Starts from here to here. Then again, here is the wave from here to here. Look, the same pattern. So this is a regular wave, but it doesn't give a pure one frequency. Notes consist of a main fundamental frequency mixed with others called overtones, which are usually weaker and have frequencies that are exact multiples of the fundamental. That's why we have different quality or timbre. The number and strength of overtones decides the quality of a note. A violin has more and stronger, higher overtones than a piano. So, we are talking about fundamental frequency and overtones. As I said, this is a regular vibration. This is a note. But because why? We have a regular pattern, but it doesn't give the same as now a tuning fork, for example, the same sound as a piano. Even though they have the same amplitude, they have the same pitch, they have the same loudness, but they differ in quality. Clear? Same note on three instruments are shown. Their different shapes show that while they have the same fundamental frequency, their quality differs. So look, all of them, they have the same frequency count. The number of patterns, 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4. So I have the same number of frequencies. So the pitch is the same. Amplitude is the same. They are different only in quality. Is that clear? I hope that it's clear. Although the wave form is a transverse wave, it represents a longitudinal sound wave. So here, as I said before, okay, you say teacher, here why they are transverse? As I said, they are just representing the sound wave, but the real sound wave is a longitudinal wave. Okay, that's all for today. I hope everything is clear. Thank you, dear.